All right, welcome to The Explainer. Today, we are diving deep into an invisible force that, well, it pretty much glues our entire universe together. I mean, it's what keeps your feet planted on the ground, but it's also what holds entire galaxies in this grand cosmic dance. We're talking, of course, about gravitation.
Okay, so let's jump right in with a question. One that supposedly hit Isaac Newton, as he was just sitting there watching an apple fall from a tree. What in the world could a falling apple have in common with the moon just hanging up there in the night sky? Turns out the answer to that wasn't just some neat little puzzle. It was about to completely rewrite how we understood the entire cosmos. And this is where Newton's genius really shines. He connected these two things that seemed totally unrelated, right? An apple falling and the moon orbiting. He had this incredible idea. What if the exact same force that yanks that apple to the ground is also the one that's keeping the moon locked in its path around the Earth? So get this, Newton figured out the moon isn't just floating, it's actually in a constant state of falling toward us, just like the apple. The big difference, the reason it doesn't crash into us, is that the moon also has this huge amount of sideways speed. So as it falls, it's also moving forward, constantly missing the Earth. And that continuous falling and missing is what we call an orbit.
Now, this constant inward pull, the thing that keeps bending an object's path into a curve, that's got a name. It's called centripetal force. It literally means center-seeking. A perfect way to think about it is just spinning a ball on a string. You feel that tension, right? That pull on the string? That is the centripetal force. And it's the only thing stopping that ball from just flying off in a straight line. Okay, but with the moon, there's no actual string, obviously. So what's doing the pulling? Well, it's Earth's gravity. You can think of it like this invisible tether, this invisible string that provides that constant centripetal force. And that's what's needed to bend the moon's path into that endless, perpetual orbit around us.
This brings up a pretty good question, though. If the Earth is pulling on the apple, does the apple also pull back on the Earth? And according to Newton's famous third law of motion, for every action, there's an equal and opposite reaction, the answer is absolutely yes. So why don't we see the whole planet jump up to meet a falling apple?
And here's the key. The forces are equal, yeah, but their effects are totally different. It all comes down to Newton's second law, which tells us that acceleration is just force divided by mass. Since the Earth's mass is just astronomical compared to a little apple, the acceleration the Earth feels is so tiny that it's completely impossible to even notice. So putting all this together led Newton to this massive idea, a universal rulebook, basically, a law that doesn't just apply to apples and moons, but to every single object in the entire universe. We're talking from the tiniest fleck of dust to the biggest galaxies out there. And this is the very heart of Newton's universal law of gravitation. And think about how bold this statement is. It's basically saying that you, the screen you're looking at, and some star billions of light years away, you're all pulling on each other, right now. It's happening at this very moment. So, what decides how strong that pull is? Well, it really boils down to two main things. First, mass. It's super simple. The more mass something has, the stronger its gravitational pull. Second, and this one is a really big deal, is distance. The force gets weaker, and it gets weaker dramatically the farther apart things are. It follows what's called an inverse square law. All that means is if you double the distance between two things, the gravity between them doesn't just get cut in half. It drops all the way down to 1/4 of what it was. Huge difference. Okay, so this universal law has a really personal effect on every single one of us. And it brings us to something that, honestly, trips a lot of people up. The difference between mass and weight. They're not the same thing. All right, so when something is in free fall, it means it's accelerating just because of gravity and nothing else. And here near the Earth's surface, that acceleration is pretty much constant. We even give it a nickname, g. It's about 9.8 meters per second squared. And this constant pull is exactly what gives things their weight. And get this, if you could get rid of air resistance, a feather and a bowling ball would fall at the exact same rate. So let's really break it down. Your mass, that's the amount of stuff you are made of. Your atoms, your molecules, that number is constant. It's the same whether you're here on Earth, chilling on the moon, or floating out in the middle of deep space. Your weight, on the other hand, is the force of gravity pulling on all that stuff. And since the force of gravity is different in different places, your weight can change all over the place. And this number right here really drives that point home. 1/6. If you were standing on the moon, you would weigh only about 1/6 of what you weigh here on Earth.
But, and this is the important part, your mass, the actual amount of you, hasn't changed one bit. It's just that the moon's gravitational pull is a whole lot weaker.
So we know gravity is always pulling things down, giving them weight. But, it's not the only force in the game. Let's take a look at how gravity interacts with some other forces, because it helps explain some everyday things that are actually kind of puzzling when you think about them.
Like this one. Why does a gigantic steel ship float, but a tiny little steel nail just sinks like a rock? I mean, they're both made of steel, which is way denser than water, so what gives? To figure this out, we've got to talk about two things: pressure and buoyancy.
Okay, first up, pressure. Pressure is really just about how spread out a force is. You can have the same exact force, but if you change the area it's pushing on, you get a totally different effect. Think about a sharp knife. Why does it cut so well? Because all the force you're using is focused on that teeny tiny edge, creating a huge amount of pressure.
Now, pressure is important for sure, but when we're talking about things in fluids like water, the real heavyweight champion that fights against gravity to decide if something sinks or floats is density. And all density is how much stuff you can cram into a certain amount of space. And really, the rule is super simple. If an object is denser than the liquid it's in, it sinks. If it's less dense, it floats. That's it. A solid steel nail, way denser than water. So it sinks. But that massive ship, it's not a solid block of steel, is it? It's a carefully shaped hull that's filled with a whole lot of air. So its average density, you take the steel and all that air, is actually less than water's density, and that's why it floats.
Okay, let's zoom back out from ships and nails and just take a moment to appreciate how incredibly profound this one simple law of attraction really is. It literally governs the entire universe. I mean, think about it. The force that's keeping you in your chair right now is the same one that dictates the moon's orbit. It's the same one that choreographs the dance of the planets around the sun. And it's even responsible for the tides pulling on our oceans. Everything comes down to this one force. Gravity really is the universe's grand architect. But here's the really wild part. On our scale, the human scale, gravity is ridiculously weak. I mean, think about it. You overcome the entire gravitational pull of planet Earth every single time you just pick up a pen. But when you zoom out to the cosmic scale, it becomes the undisputed champion, the most dominant force out there. And that's just because mass, and therefore gravity, always adds up. It never pushes away.
And that leaves us with one final, kind of mind-bending thought to chew on. We know of 4 fundamental forces in the universe, and gravity is by far the weakest of them all. I mean, it's not even close. And yet, it's the one that dictates the shape and structure of planets, of stars, of entire galaxies. So the question is, why? Why does this gentle, persistent, and oh-so-weak force have such an enormous, world-shaping impact on absolutely everything?